So, hi, my name is Adam, and today I'm going to be talking about everyone's favorite topic, Python packaging. So, who am I to talk about this kind of stuff? Well, I've been using Nix for going on 10 years now, so pretty old in the game. I got commit bit back in late 2017 to Nix packages, so if you have contributed to Nix packages a lot back then, I probably reviewed some of your PRs. If not, I haven't done so much lately. Been working full-time or on and off for Nix since 2018, so I've been a Nix consultant since then. Right now, I'm doing freelancing type work at exactly the kind of thing I'm going to be talking about. So if it sounds cool to you or your company, then contact me, please. Yeah, so in my previous life, I was a full-time Python developer, which is how I got into this kind of intersection of both of Nix and Python. So I'm author of a lot of tooling in the space. So if you've used Nix about jobs or pyproject.nix, this kind of thing is mine. Nix unit, the unit testing suite using the C++ evaluator is also a project of mine. So yeah, I've been doing quite a lot in this space. So Python package management has a reputation of looking like this, but we're going to start making some sense of the landscape and go through some historical legacy so that you gain an understanding for what we're talking about. And then we'll dig more into how this applies to Nix and what I had to do to get there. And then we'll look at some code examples of how to develop using these tools I've developed. So broadly, you can divide the Python landscape into a few different kinds of tools. Some of them are build systems. So if you are familiar with setup.py, like distutil/setup tools, these are kind of living in that space. In the last couple of years, like 5-10 years, there has been a lot of movement in standardizing these things. So setup.py was kind of more of a rumor than a standard, and nowadays we're getting more and more into standards and like standardized behavior, even in the Python world, which traditionally looks like this. So this is used by many, like this pyproject.toml standard is defined in 2 different standards that are relevant to us today, PEPs 517 and 621. So this build system standard, the first one there, is used by pretty much every Python build system out there today, including setup tools like the guy that introduced setup.py. Then we have project and environment manager. So if you've been working with Python in the past, you have probably used pip, well, maybe Poetry or PDM or UV. Well, these are tools that live one layer up in the stack and provides you with like the developer tooling that you would normally invoke. And then traditionally, these tools don't have lock files. So Poetry kind of introduced that, kind of pioneered that in the Python space. But nowadays, there are a plethora of other tools, and we will particularly talk about UV later, but just mentioning that this has been a long time coming, and there has been a lot of incremental improvement in the space. Yeah, I mentioned previously already, this is standardized in various PEPs. And then there's this massive packaging repository, PyPI, where almost all of the relevant packages that you would use on a day-to-day basis lives. They distribute both in binary form and in source code form. So binary form, those are called wheels, and in source code form, they are called source dists or sdists. Python dependency specifications, they are not exactly simple. So while you may normally see just a name of a package, this is the full grammar of like what you can do with this. This is even omitting some stuff. So we can take a look here at this request here. That's the package name. We want this request with optional features, security, and tests. We want any version 2.8.1 or above, but any other one may match. And then we have this very competent but highly complex platform compatibility algebra. And that is we're gonna talk more about that later, but that has been one of the biggest challenges of implementing all of this to be able to execute this from Nix. This dependency specification format is also defined in a PEP 508. Python is not using semver either, so they have their own version format, which is highly complex as well. So we're starting with the more reasonable version numbers with like 1.0.0, but then we go on to like have beta releases, which is not exactly semver, and go even further to have post releases, and then you also have this thing called epochs, which is at the very end here. So this means 1.3.4.5, epoch 4, so like an epoch means that like anything with an epoch takes precedence over anything else. So even if there was a 2.0 release that had a smaller epoch than number 4, this would be considered older. So yeah, so you can have a post release of an alpha release. This is perfectly fine in the Python world. This platform algebra is like a whole mini programming language in itself, kind of, but it can only evaluate to either true or false. So we can see here how we can use that to affect whether we want to install a certain version of a dependency on one platform or another one on a completely different platform. So this includes everything from like whether you're on Linux or Darwin, which CPU architecture, which implementation of Python, because there are many of them. I mean, there's only one that people really use day to day, but there are many of them that are actually relevant from the perspective of checking cross-platform dependencies. So yeah, this is how the kind of the metadata formats in the Python world started out. We had setup.py. This is already a bit problematic because, well, project metadata is Python code. The only way you can properly read this file is by executing Python code. So there is no way for us to kind of say that, oh, this dependency is required without actually running the build steps required to figure out that is what we need. Another thing that is problematic is that, well, this is not a standard. This was just setup tools introducing this as a kind of idiom, but there's no real like standardization effort around this. You typically develop these applications with pip install-e, which is quite an interesting bit that will not build the actual package you are developing. It will build a stub of that package with a pointer into your source tree, so you can hack on it interactively. You don't have to rebuild the thing to see the results. At some point, well, someone came up with the idea that this is not very nice from a development perspective. Well, we want to be able to install something like a little bit quick and dirty. So this format requirements.txt was dreamt up, which is pretty much a list of these pep5way dependency strings. So you would typically invoke this with pip install-r requirements.txt, and that would install all the dependencies that you need in your development environment. Often used alongside setup.py, so setup.py would kind of read this requirements text so that you don't have two places where you constantly need to keep this in sync. So this not being standardized became a bit of a problem, especially when we got more and more complex build systems. We got build systems that can build C code. We got like Mason, for example, that can automatically build Python bindings for C code. We have Maturin that can do the same for Rust. We need a standardized way for a Python builder to invoke its build system, even though we don't know what that build system is necessarily upfront when we start the build. So we got this static pyproject.toml file that was introduced first just as a build system entry point and declaration thing, but then later it was expanded with even more things by Poetry that kind of pioneered this aspect of being able to not just describe what do I need to build this thing, but what do I need to run this? What is the whole like runtime dependencies, and describing the whole project in this file. Sadly, they also introduced a few non-standard version comparison operators and so on and so forth. But nowadays, we have a standard PEP621, which completely standardizes this. So we can see the previous description here lives in the tool.poetry namespace, but nowadays it's just a just a top-level project table where everything lives, where we can describe everything from like our dependencies, which are these complex strings that we saw before, optional dependencies, what scripts does this thing output, like what things does it provide that you can actually run, and this is completely standardized in a way that we can consume. Like, so nowadays, UV has kind of taken the crown as the premier Python developer tooling in the space. It builds upon these standards. So it implements like this PEP621. You still use this to describe your projects. But what's interesting about this guy compared to every other thing we saw up here, here we go, is that they are actually trying to make a bit sense of this and remove some nodes from this graph by implementing everything in a single tool. So this doesn't just include dependency locking and like high-level project management. It also includes the lower-level stuff like how do I build these binary wheels? Well, UV can do that without the use of any of the existing build tooling that are all implemented in Python, which introduces a weird bootstrapping dependency. So if you need a Python module to be able to build your Python modules and to install your Python modules, well, you have a bit of a weird bootstrapping problem on your hands, but UV completely just eliminates that by implementing all of this in Rust. It replaces a bunch of different tools in the space, so you don't no longer have to know all of these like 5, 10 different tools. You can use the one tool. And being written in Rust, it's very fast. That's kind of their main selling point. I think it's the least interesting selling point of theirs, but it is indeed very fast. And they aim to be like Cargo for Python. So the development experience of Cargo, where you don't need to care so much, like what does this depend on, what versions, etc. It just like works. From their perspective, they also download a Python interpreter that matches your project. Version constraints, we are not going to be interested in that from the Nix side of things, but indeed it does solve the kind of bootstrapping of interpreters as well. It already accounts for over 10% of all the PyPI traffic, so this is not just a small like new tool that's coming into the space, it's taking over in a big way. It introduces monorepo tooling, so all the previous tooling could only handle like one top-level package at a time, while UV is designed for monorepos as well. And they don't like introduce new stuff invented at home. They are completely based on all of these packaging standards. So it goes into standards first and then implemented by UV. So UV kind of looks like any other kind of developer tooling that you would expect. Just showing you this so that you see that like there's nothing weird about this. You can create projects, add dependencies, lock, and also do these kind of lower level. So these are things you don't normally care about as a user, but that excites me a lot because of the bootstrapping. And well, I mentioned that they also include monorepo tooling. So this, instead of having a single top-level pyproject.toml, you can with your project inside, well, now you can have this one, this little stub here that says, oh, they include all of these packages, and then your packages are just regular Python packages. So but you can co-develop all of these. So I mentioned this editable stub before. If you install a UV project, it will not just give you one editable stub for your one leaf package. It will give you an editable stub for every single local package, so you can co-develop them together. And now we get into the Nixy side of things. And this is what I've been working a lot on. So with Python being as complex as it is and having all of these packaging standards, and me being an author of Poetry.to.nix previously, having struggled with this, I wanted a better toolkit to be able to write Python.to.nix tooling quickly and have a broader set of use cases for that than what Poetry.to.nix could ever provide. So was about 2 years ago, I started hacking on this standardization effort. So, implementing all of these packaging standards one by one in pure Nix code. And it all has also resulted in a re-implementation of all the Nix build system things. So if you've used build Python package from Nix packages previously, or like this with packages, all of this is completely re-implemented here in a way that is much more Pythonic. I will show you in a second what that looks like. There's no input from derivation here. Everything that will be talking about here is implemented in pure Nix code with no input from derivation. First, well, these complex version numbers, to be able to even compare these, to be able to do dependency, like install time dependency resolution, we need to be able to compare these things. So we have a parser for that in pure Nix. For the most part, this is implemented using like clever regexes and stuff, but yeah, we have a full data structure that we can compare. Like, so this actually works pretty well. So we can compare, like we can see that this 1.0 post 1 release is indeed larger than this one, and this whole API mimics built-in compare versions from Nix. So if you've used that before, then you know how to use this. It's just that you also need to parse the versions first. So here, this was the biggest challenge by far of implementing any of this PEP508 platform compatibility algebra. And faced with this problem, well, you do what any sane and reasonable person do. You implement a full recursive descent parser in pure Nix. So this is implemented like as a tokenizer, working character by character, and building up a token structure that is then lexed and everything. So we can also parse these not just the platform algebra, so this is what it would look like. Like this is what it looks like after we parse the whole dependency specification string. Yeah, I'm just gonna, okay. And we can evaluate these markers. So we can make this, make an environment to evaluate these markers. We can parse them and we evaluate them. And well, we can see that our Python 3.12 is indeed smaller than Python version 3.11. We also need to be able to parse these wheel file names. They contain information about which wheels are compatible with which platform, and we need to be able to compare this with the platform that we are trying to run this against. So we will look at a uv2nix file in a second where this becomes relevant, but just know that we also need to be able to parse these files and compare the ABI and the language tags. So here we can see like this would be a typical kind of contents of a package manager log file, and then we want to solve for what do we need for this particular environment, and not just solve for what is compatible, but also sort them by which is the highest compatible tag, so that we get the best kind of newest glibc version. So technically speaking, there's two different versions here that are compatible with our Linux environment. One is this, and the other one is this. Well, and we want to make sure that this one actually comes first because it's a higher glibc version. So you can use like fancier features of glibc. We also implemented a complete meta build, like a Python meta build system. So we're in uv2nix. I'm not using any of the Nix packages Python infrastructure. This is because Python dependencies can be circular, and Nix, as many people know, you can't model a circular dependency graph using just derivations, but we can do so using late binding. So if you look at this build Python package, like how you would build things with Nix packages example here, we can see that, well, we have propagated build inputs. These are added to the build like at build time, and then we have the build system there. But in my model instead, well, we're just using standard make and the derivation, and we stick our dependencies in pass-through instead. So this means that runtime dependencies will not be available at build time. But what we can do instead is in the evaluator, when we want to create an environment, well, then we need to solve for what is the runtime dependencies of this thing. So the whole build graph becomes, instead of this like pyramid-shaped thing, it's like a flat list of everything that you need, and then you just go into the same environment to be a coherent thing that works together. We're not using any Python path like machinery or anything like that. This is all because there's no propagation, like we don't have the hooks that can set up any Python path. Because you don't have runtime dependencies at build time, well, you also end up rebuilding a lot less. Because like, just because you depend on NumPy doesn't mean that we need to rebuild your application. We just link in another NumPy into the runtime environment. And we use standard virtual environments, which means that things like LSPs, like Pyproject, will just work out of the box. If you try to use this with the Nix packages, environments, like with packages, you're going to have to orchestrate and instrument that a bit yourself, but this will just work. So let's look at what is a typical like, what does it look like to develop Python packages with Nix packages? Well, we have these 3 files here. Well, one is our pyproject.toml describing our project. The other 2 are a default.nix, a package build, and a shell describing like what do we need to develop this. This is already a bit problematic because we need to repeat ourselves quite a lot. We see that we are losing a bit of fidelity here, so like we no longer have these version constraints here anymore. There's no way to express that on the Nix side of things. Well, we need to repeat everything twice, once for the package build, once for the development environment, and this isn't very nice. So, but with pyproject.nix, what we can do instead is we can just load this pyproject.toml file up. So we have a higher level project abstraction. This project abstraction like parses and holds all the relevant content of the project. And this is just like your regular boilerplate. We select the package set and a Python interpreter, and then we can see here that we instead of manually typing out like this is the packages that we need, we just say render this project as a with packages argument, and then we call Python with packages. And a similar thing again for rendering the attributes that we use for the package build. So now we don't need to repeat anything. Like now the pyproject.toml is our single source of truth. Well, this is still not like ideal because whatever Python like dependency constraints here, like this will be ignored. So pyproject.nix has tooling to assert this, but it's opt-in. But what's really cool here is that we don't need to repeat anything, and we can just use the standard Python standards that we are used to. We have the same project abstraction for loading up requirements.txt. So we see here like this looks almost identical. It's just like calling a different function, but the structure that it returns is the same. So we can use it the same down here. So it unifies like all these standards in a way that you can develop your projects. But this is still using Nix packages. So whatever dependency, like version constraints or other things that you have there, it will be ignored. So taking things a step further, we can develop not just like pull in a bunch of packages, but we can also build this stub, like this editable stub ourselves. And this will point into our development source tree. So we can render this project not just as like a with packages argument, but also a with packages argument that contains this editable package that we need. So this will make sure that this project of scripts here is available in our development shell. So if we enter this development shell, we will be able to call this trivial thing just as trivial instead of calling the full python-m trivial.main. And all of this tooling has then later culminated in uv2nix. So using this UV package manager together with Nix, marrying the two at the hip essentially. So it's heavily based on all the stuff that I've been talking about in pyproject.nix. I consider this like the flagship project of the ecosystem. It's a spiritual successor to poetry.nix, but it's far more competent in what you can do with it, and it exposes that, like, it exposes those lower level layers more than the previous thing did. So let's take a look at what does a typical package entry of this uv.lock look like. So now that we know a little bit about the ecosystem and what challenges we have, so we know that, for example, like this cryptography package, well, we only want to install it's the CFFI dependency if we are not on PyPy. If we want to build it from source, this is the relevant file. Well, and if we want to just install the binary artifact from PyPI, then we need to go through this list of the wheels here and filter out which one is the correct one for our platform. But now this is fairly easy. When we have all this other tooling to do this, it's fairly easy to just walk this uv.lock, do a runtime dependency solving of like which is the relevant package versions for my particular environment. And this is what uv2nix provides. So as we previously saw in the project, like the project abstraction, uv2nix introduces another abstraction on top of the project abstraction, which is a workspace, which is essentially the same thing as a project. It just holds many projects that are from your log file instead of holding a single project from your pyproject.toml file. So then we can automatically create a package overlay from this, where we say that we want to use a wheel whenever it is, like this binary artifacts, whenever it is available, but we want, like, it will fall back to using source disks whenever that is not available. And then we compose that together with a package set. So this is using pyproject.nix here to create the base package set structure, but then we hook in the uv2nix overlay on top of that. And then we can just like render that out as a Python virtual environment, or which is our like runtime like our build production artifact, or we can render that out as a development shells, again, where every single package that you have available locally is an editable package using this stub and pointer methodology. But we extend the Python facility with using environment variables that are expanded at runtime, like this repo root here. So otherwise, these stub files, they contain exact, like, absolute paths to your development tree, not just like not a relative path. So this environment variable methodology is used to make that more pluggable. And whenever things, like, there are things, obviously, like native dependencies, which are not available in your log files, or your dependencies, build system dependencies, they're also not available in the log files, so you might have to supplement that, but this is how you can do that. And again, because of the late binding thing, we need to resolve our build systems, because otherwise, a runtime dependency of setup tools would not be available in the build time environment. Well, I think I'm almost done. I've been talking a lot, I feel like, already, but some takeaways here is, well, Python packaging is a very complex landscape, but it's also like, I think it has a bad rep, not just because, like, not because it's bad, but because it's complex by necessity, and because it exposes the underlying fact that most Python packages are like not just existing as Python, they are also like binding to C and Rust dependencies. So it's exposing all of the complexity of all of those ecosystems, not just Python. There's a spectrum of possibilities here. Like, so obviously, if you're on a team with a bunch of other Python developers and you are not using Nix for doing production builds, I wouldn't recommend any of this for you. Just keep doing what you're doing with your impure development shells. This is really for if you want to be a Python developer and ship stuff with Nix. And I'm done. And if you have any questions, on the left, the QR code on the left there goes to my website. The QR code on the right there goes to the org that holds all of these pyproject.nix and uv2nix projects. And yeah, anyone has any questions? So the question was, after exploring the design space for this much, what's my thought on what Nix packages should do with all of its Python libraries and stuff? So I'm going to have a bit of a hot take here and say that most of it should be yeeted from orbit. No, I think being a Python developer, developing on top of Nix packages is not a good enough experience. You're gonna struggle a lot with packaging like your custom stuff on top of that. You're gonna really feel the packages that are missing. So I think we should reconsider who is even this Python package that's for in Nix packages. What is it there for? My take is that it's only there to support Nix OS and its use cases, and we should own that and just be open and honest about it, instead of just keep growing this mutually compatible set that is like a false promise, in my opinion. The question was, do I have a standard big list for all the common overrides? No, I do not, but I am working on better automation for automatically creating overrides for the common case. So in the cases where we are overriding build systems or native dependencies, well, mostly we can actually infer that through static analysis. We can look at the source distribution to see which build system dependencies this thing has, and we can look at the binary wheels and actually like look at the elf headers, what does this thing link against, and figure out what native dependencies we have. So I've been working on that instead. I do not, like, working on a big list of overrides is inherently ephemeral. Like the work you're doing is going to break at some point when the ecosystem moves forward. So I think it's much better to focus on building better automation than it is to work on something like an overrides list, which is eventually going to break anyway.